Have you ever run into a problem that's so complex the only way to solve it is to, well, ask for the answer to a slightly simpler version of the exact same problem? It sounds kind of like cheating, right? But it's actually one of the most powerful and elegant ideas in all of computer science. Okay, let's dive into this mind-bending concept, recursion. So to get our heads around this, let's start with a simple question. If I asked you to add up all the numbers from 1 to 100, how would you go about it? I mean, you could just grab a calculator and go 1 plus 2 plus 3 and keep going 100 times. And that works for sure. But there's a much more interesting, almost lazy way to think about this. And this clever approach, it's more than just a party trick. It's the key that unlocks a whole new way of thinking about problems. Okay, so picture this. You're in a classroom, and your job is to get the sum of numbers up to 100. Instead of doing all that work yourself, you turn to your friend and ask, hey, what's the sum of all the numbers from 1 to 99? Now here's the crucial part. You just have to trust that they'll get you the right answer. Once they hand you that number, all you have to do is one tiny piece of work. Add your number, 100, to whatever they gave you. And that's it. You're done. And that right there, that's the big idea. The solution to our big problem, the sum to 100, depends on the solution to a slightly smaller identical problem, the sum to 99. And what did your classmate probably do? They probably turned to their friend and asked for the sum up to 98. This chain of passing the buck, that's the heart of recursion. So this whole delegation thing isn't just a cute trick. It's a formal strategy, and it only works because it follows two fundamental, non-negotiable rules. Let's break those down. So here's the textbook definition. Recursion is just the process of defining a problem using a simpler version of itself, exactly like we defined our sum to 100 problem by using the answer to the sum to 99 problem. For this whole thing not to fall apart, you need two things. First, you need the recursive step. This is the rule for delegation. It's how you keep the chain going. For any number n, the rule is simple. Ask for the sum to n minus 1, then add your own number n. But, this can't go on forever. You need a stop sign. That's the second rule, the base case. This is the point where the questions stop. For us, that's when you finally get down to the number 1. The sum of the first number is, well, it's just 1. There's no one else to ask. The chain reaction is over. Okay, this is all great for people in a classroom, but how do we teach a computer to be this clever? How do we actually get a machine to execute this strategy all on its own? Well, you can actually see those two rules right here in the code. See that if n equals 1 part? That's our base case. That is the hard stop. It tells the computer, if you get to 1, you're done. Just return 1. And the else part? That's our recursive step. That's the part that tells the computer to call the exact same function again, but this time on a slightly smaller problem, n minus 1. To really get a feel for this, let's walk through what the computer actually does when we ask it to run this function for, say, the number 4. It's exactly like that chain of classmates asking each other for help. All right, so first we call the function with 4. The computer checks. Is 4 equal to 1? Nope. So it goes to the recursive step. It says, okay, I need to return 4 plus whatever the answer to sum of 3 is. So it has to pause what it's doing and makes another call. So now the function is running for the number 3. It also pauses saying, I'm going to need 3 plus whatever sum of 2 gives me, and it makes yet another call. And sum2 does the exact same thing. It puts itself on hold while it calls down the chain one last time to sum1. At this point, we've got this whole stack of functions, each one just waiting for an answer from the one below it. And then we finally hit it. The function gets called with the number 1. It checks the condition if n equals 1. And it's true. The base case is hit. The dominoes stop falling. It doesn't need to call anyone else. It has the answer. It just returns the value 1. This is the first real concrete answer in the whole process. And now everything starts to unwind. The answers start flowing back up the chain. The sum2 function, which was waiting, gets that 1 back. It can finally finish its job. 2 plus 1 is 3. It returns 3. Now sum3 gets that 3, does its math. 3 plus 3 is 6, and it returns 6. Finally, our original function call sum4 gets the 6, calculates 4 plus 6, and returns the final answer, 10. Okay, so summing numbers is cool, but that's really just scratching the surface.
Where recursion really shines is in problems that feel way more complicated, like, say, finding your way out of a maze.
Seriously, think about it. How would you program a robot to solve a complex maze? You could try to write this massive, insane set of rules for every possible turn and dead end, but what a nightmare. Or you could think recursively.
A recursive strategy for a maze is incredibly elegant. Here's how it works. At any spot, you pick a direction you haven't tried yet and you move there. Then, you delegate. You make a recursive call that basically asks, hey, can you solve the maze from this new spot? If that call eventually comes back and says, yes, I found the exit, then you're done. But if it comes back and says, nope, this was a total dead end, you just backtrack. You undo your move and try a different direction.
You see that? It's the exact same core idea. You're not trying to solve the entire maze all at once. You are only responsible for taking a single step, and you simply trust the recursion to figure out the rest of the journey from there. It's a leap of faith. So, when you step back, what's the big takeaway here? Recursion isn't just some niche programming technique. It's a completely different and powerful way to frame problems. This whole approach, this pattern, actually has a name. It's called divide and conquer. Whether you're adding up numbers or sorting a huge list of data or navigating a maze, the strategy is the same. You take a big, difficult problem and you just keep breaking it down into smaller, easier versions of itself until you get to a version that's so simple you can solve it instantly. And to really get comfortable with this way of thinking, you have to take what programmers call the recursive leap of faith. You have to just trust that your function is going to work on the smaller problem, even if you haven't fully traced it all out. You focus on making sure your one step is correct, and you trust the chain of delegation to handle the rest. You know, the amazing thing is once you train your brain to see this pattern of self-reference, you start seeing it absolutely everywhere. In the way a tree branches out, in the intricate structure of a snowflake, or in the endless reflections between two mirrors. So I'll leave you with this question. Now that you can see this pattern of big things being made up of smaller versions of themselves, where else are you going to find it?